Tom class of eta cap that push the image of rho under the Hurewicz map equals the fundamental class of the geometric Poincare complex. Well, so H goes from pi star of the Tom space to H star of the Tom space. So this is somehow the Tom view of this. Yeah. So what I mean by this is probably if I is the inclusion of X into the Tom space as a zero section, this is the inverse of I star, which is an isomorphism. Clear? So this looks similar to the condition in the definition of a spherical of a Spivak normal structure. Yeah. And in fact, we will see that this is somehow having a normal. Well, apart from the fact that eta is a normal is a vector bundle, not a spherical vibration, but this will be equivalent. A reduction of in the next theorem, a reduction of a spherical of the Spivak normal bundle to a vector bundle will be equivalent to the existence of a normal invariant. Okay, so two such things are equivalent if there is a stable bundle isomorphism between eta and eta prime, so stable bundle isomorphism, eta prime plus some trivial bundle eta epsilon L, such that, well, under the induced map of Tom spaces, this element is mapped to this element. Yeah. So T C star goes from this stable homotopic group so M plus K plus J, well, J large so what is this? K plus J is K prime if this is the dimension of eta prime plus L, so this is M plus K plus L. Well, J, L are big enough, so this is the M plus Kth stable homotopy group of the Tom space of eta, and this is the M plus K prime stable homotopy group of T eta prime, and so rho is mapped to rho prime. Yeah. So two normal invariants are equivalent if there is a stable isomorphism between eta and eta prime, and the induced map on the Tom spaces maps rho to rho prime. Okay, let me abbreviate by Tx the set of normal structures up to modular equivalence, the set of well, the normal structure set, the normal structure set as the set of equivalence classes of normal invariants. Yeah? Okay, this might look a bit confusing, but let's look at an example. If you have an m-dimensional manifold, we can embed it into a high-dimensional sphere, certainly. Well, we also have a so we can take the normal bundle, the unstable normal bundle of M in the sphere. We can look at the regular neighborhood, at the tubular neighborhood. We can look at this map, this sort of projection to regular neighborhood modular boundary. This is the Thom space. This is the Thom space of the normal bundle. So this is P, and this is somehow, well, this is the inclusion at zero section. Okay, so claim is nu m comma P is a normal invariant, is a normal invariant of M. Well, so the only condition we have to check is the one I already, no, here. And this is quite straightforward. I mean, this is true for manifolds. So the Thom class of eta. So what is the Thom class of eta? The Thom class is the push forward of the fundamental class of M, and then the dual here. So let me denote it by D. Yeah? So usual notation, D is the inverse of the isomorphism capping with the Thom class, well, with the fundamental class of this. Yeah, this is this map. So what I have to check is D I star M cap H star of P equals M. Well, or equals I star of M. So you remember I wrote I star inverse here. So, well, what is this? H star of P. This is just the push forward of the fundamental class of the sphere. So this is just H. This is just P star of the fundamental class of the sphere. Well, and this map is certainly of degree 1. Yeah? So this is just. So what we do is we take D, and then we take the inverse of D. This is quite obvious. Yeah? Just by construction of the Thom class. Well, in fact, any two normal bundles give equivalent normal invariants, because any two normal bundles, well, coming from embeddings like this, are stably equivalent. And then we only have to check the consistencies here, but it works as well because everything is degree 1. So this is the canonical normal invariant of a manifold. Okay. Questions, by the way? No? We can have a break here if you want. No? Okay, start again. Okay, let us come to the theorem. By Browder and Novikov. So if we start with an n-dimensional geometric Poincare complex, the following are equivalent.